Put your hand out the window of a moving car, tilt it slightly, and suddenly the air feels like a solid object pushing back, not just brushing your skin, pushing. You can almost lean on it. Now here's the strange part. The air is mostly empty space. It's made of tiny molecules zipping around, and yet it can feel like a wall if you move fast enough. So what are you actually feeling? In school, pressure is usually introduced as a neat little formula. Force divided by area. And then everyone moves on like that's the whole story. Pressure equals F over A, easy. And technically, it's true. But it's also like defining music as air vibrations per second. Yes, that's a definition. But it's not what music really is. It doesn't explain why it makes you feel something. It doesn't explain where it comes from. It doesn't explain how it behaves when you change the room, or the instrument, or the listener. Pressure is the same. The formula isn't the explanation. The formula is the shadow cast by the explanation. If I told you speed is distance divided by time, you'd still ask, what's actually moving? What mechanism produces that speed? If I told you temperature is average kinetic energy, you'd still ask, why does that make things expand? Why does it flow from hot to cold? So if pressure is force per area, the next question is obvious. What is doing the pushing? Because pressure isn't a substance inside a gas. It's not a thing stored in water like some kind of invisible syrup. It's not a magical property that fluids have because the textbook said so. Pressure is something much more physical and much more surprising. It's what motion becomes when it's trapped. Let's start by taking the most familiar case, gas pressure. Not because gases are the only kind of pressure, but because gases show the mechanism in the cleanest possible way. Imagine a room full of invisible 10 NIS balls, each one slamming into the walls millions of times a second. That's not a metaphor yet. That's literally the kind of thing happening in air, except the tennis balls are molecules and they're smaller than anything you can picture, and they're not moving like slow drifting dust. They're screaming around at hundreds of meters per second, even when the air feels perfectly still. You've probably heard this before. Gas pressure comes from molecules colliding with the walls. But most explanations stop right there, as if saying collisions is an explanation the way saying gravity is an explanation. What matters is what a collision does. A molecule hits the wall. It bounces. That means its momentum changes. Momentum is mass times velocity. The molecule comes in with momentum toward the wall, and it leaves with momentum away from the wall. That's a change in momentum, and by Newton's laws, a change in momentum requires a force. The wall exerts a force on the molecule to reverse it, and the molecule exerts an equal and opposite force on the wall. One collision is tiny, but there are an absurd number of molecules. In 1 cubic centimeter of air, about the size of a sugar cube, there are around 25 billion molecules. That's a number so large your brain can't really hold it. Even billions starts to feel like nothing. So the wall is being struck by a storm of momentum changes. A non-stop hail of microscopic kicks. The wall feels that as a steady push. That steady push per unit area is pressure. So pressure in a gas is not just force over area. It is the rate at which momentum is delivered to a surface, divided by area. That's the deeper meaning. And that's already a huge upgrade, because now pressure is not mysterious. It's not a static thing. It's a dynamic average. It's a statistical result of chaos. And it has a satisfying physical bite. Pressure is what happens when motion keeps getting redirected by boundaries. Now you might say, okay, fine, that explains gas pressure. But liquids are different, right? Liquids aren't full of free-flying particles, and solids aren't either. So how can pressure possibly be the same concept? Before we go there, let's confront one of the strangest facts about pressure, a fact that most people memorize without ever realizing how bizarre it is. Here's the part that should bother you. If gravity pulls down, why does water push sideways? Take a glass aquarium, fill it with water. The water pushes outward on the walls, not just downward on the bottom. In fact, the deeper you go, the more it pushes sideways. But gravity is vertical. Gravity isn't pulling water sideways, so why is the sideways pressure greater at greater depth? This is a moment where the force per area definition becomes useless, because it doesn't tell you where the force comes from. It only tells you how to measure the result after the force is already there. The real answer starts with the microscopic picture again. But now we need to think about liquids. In a gas, molecules fly around mostly independently, like a chaotic swarm of ping-pong balls in a room. In a liquid molecule, S are still moving. They still have thermal motion. They still collide, but they're packed close together, constantly pulling and pushing on each other, like a crowd in a subway car. And this changes something important. A liquid doesn't flow freely through itself the way a gas does. If one molecule moves, it immediately bumps into others, so momentum is transmitted through the liquid as a chain of interactions. In a liquid, pressure is still about momentum transfer, but instead of molecules transferring momentum directly to the wall after long flights, they transfer momentum through their neighbors. Think of a crowd pressed inside a room with no space. People aren't sprinting across the room and slamming into the wall, but they are constantly shifting weight. And if the crowd is dense and restless, the wall still feels a push, because the motion and momentum of the crowd is being constantly redirected through contact. The key idea is, pressure is the way a medium transmits pushes in all directions. Why all directions? Because in thermal equilibrium, the microscopic motion is random. There's no preferred direction. In a gas, molecules move equally in all directions on average. In a liquid, molecular motion is still chaotic and directionless on average. So the momentum transfer happens in every direction. If it didn't, you'd have a net flow, you'd have a drift. But in equilibrium, everything balances. That's why pressure pushes sideways. And that also hints at something deeper. Pressure is a scalar description of something more complicated, stress, which in its full form is directional. But in a fluid at rest, stress becomes isotropic. That means it looks the same in every direction, so it can be described by a single number, pressure. So water pushes sideways because the microscopic pushes are happening sideways too, and because those pushes are transmitted through the liquid. Gravity enters not by creating sideways forces, but by creating a pressure gradient. A gradient is just a change with depth. The deeper you go, the more weight of water is above you. That weight must be supported somehow. And the only way the water can support weight is by increasing pressure as you go down. That's the essence of hydrostatics. The pressure increases with depth because pressure is how fluids transmit the burden of weight. But again, not by storing weight as a substance, by transmitting forces through microscopic interactions. Now here's a famous principle, Pascal's principle. It says that pressure applied to a confined fluid is transmitted equally in all directions. Most textbooks present it like a magical rule, like fluids have this special ability to spread pressure evenly. But if you understand pressure as momentum transfer and constraint, Pascal's principle becomes inevitable. Imagine you have a sealed syringe. It's filled with water. The needle tip is blocked. You press on the plunger. What happens? You feel resistance. If you press harder, you feel more resistance. The force you apply creates a pressure inside the syringe. But where does that pressure exist? It exists as tiny pushes between molecules, a chain reaction. You push on the plunger pushes on the water pushes on the next layer of water, and so on. The force is transmitted through the fluid, and because the fluid molecules are jostling in all directions, the pressure spreads. Not because of magic, because if one direction had higher pressure than another in a fluid at rest, the fluid would move until it equalized. It's like a crowd again. If one part of a crowd is more compressed than another, people shift until the compression becomes more uniform, unless something prevents it. Pascal's principle is simply what equilibrium looks like in a fluid that can flow. Now that's already a much richer story than pressure is Fa. But let's go further, because the title promised something school never taught you. To deliver on that promise, we have to deal with one of the most counterintuitive things about pressure, the hydrostatic paradox. You can pour the same amount of water into two wildly different containers, and the bottom can feel exactly the same pressure. Take a container shaped like a wide bowl, then take another container shaped like a tall, narrow tube. Fill them so the water surface is at the same height above the bottom in both. If you measure pressure at the bottom, same depth, you find it's the same, even though the narrow tube contains much less water. That sounds wrong at first because you think pressure at the bottom should depend on the weight of water above it. But the formula says pressure at depth depends on density, gravity, and depth. P equals P at the surface plus rho GH. No mention of container shape, no mention of total volume. How can that be? This is where many explanations get sloppy. They just say It depends only on depth, and move on. But why? Where is the extra force coming from in the narrow tube case where there isn't as much water? The answer is beautiful, and it shows how pressure is really about force balance. In the narrow tube, yes, there is less water weight, but the walls of the container play a role. The pressure in the water pushes on the walls too. In a narrow tube, the walls are angled or close enough that they provide upward components of force that help support the water. In other words, the weight of the water is not the only thing creating forces. The container shape can redirect forces through the walls. Pressure is not simply weight per area. Pressure is a field inside the fluid and a network of forces, and the balance of those forces depends on geometry. If you want to feel this intuitively, imagine stacking books on a table. If you only look at the weight of the books, you know the table pushes up with equal force. But if you also press down on the books with your hands, the table force increases. Where did that extra weight come from? It came from you. The force balance includes the container interactions. Hydrostatic pressure is the fluid's internal way of distributing forces so that everything balances. Now let's talk about the atmosphere, because this is the example that really reveals how pressure is not just force over area. It's so something alive, something happening all the time. Right now at sea level, the air exerts a pressure of about 101,325 pascals. That number is often presented as a fact. But what does it mean physically? It means that for every square meter, the air is pushing with a force of about 101,325 newtons. That's equivalent to the weight of roughly 10 tons per square meter. So why don't you get crushed? This is one of those questions that everyone hears once, then memorizes the answer, because your body also pushes outward with equal pressure. But that's only half the story. The other half is pressure is everywhere. It's not a downward force only. It's pushing in all directions, and your body has internal pressure too, mainly from fluids and tissues, which balances it. And here's the part people don't realize. You are already adapted to this pressure. Your bones, your blood vessels, your lungs, everything evolved under it. Your body is essentially a pressurized structure, like a balloon reinforced with biology. If the air pressure suddenly vanished, you wouldn't expand like a balloon, but fluids would boil at body temperature, and gases inside you would expand violently, not because the air was holding you down, but because pressure is what keeps phases stable. Pressure affects boiling points. It affects density. It affects how materials behave. Pressure isn't just about pushing. It's a condition of matter. And this brings us to the really deep reveal. Pressure is closely tied to energy. If I told you pressure is literally energy packed into space, you'd probably think that's poetic, but it's a measurable fact. Let's go back to the gas in the room. In kinetic theory, you can relate pressure to the average kinetic energy of molecules. In fact, for an ideal gas, pressure equals 2/3 of the kinetic energy density. Energy density means energy per volume. So if you have more energy in the same volume, faster moving molecules, you get more pressure. Think about what that means. Pressure is not merely a force. Pressure is the manifestation of energy distributed through space, acting on boundaries. That's why heating a gas increases pressure. You're increasing molecular kinetic energy. Those molecules hit the walls harder and more frequently. The momentum transfer rate increases, so pressure increases. But it gets even more fascinating when you realize this isn't just about gases. Light also carries momentum. Even though it has no rest mass, it carries energy, and energy in motion carries momentum. So when light hits a surface and reflects, it transfers momentum. That means it exerts pressure. Radiation pressure is real. It's small in everyday life, but it matters in astrophysics and in technologies like solar sails. The same mechanism, momentum transfer per area per time. So pressure is not tied to weight. It's tied to momentum flow. And that means pressure appears anywhere you have momentum being redirected, whether it's molecules, photons, or even elastic waves. Now we've reached the most important point, the aha that the TT promised. So the real meaning of pressure is simple and shocking. It's what motion becomes when it's trapped. A gas molecule wants to keep going, but the wall stops it. That redirection creates pressure. A liquid molecule wants to move, but it's constrained by its neighbors and by the container. That constraint turns random motion into a steady push. A solid's atoms vibrate and repel. The lattice constrains them. That internal resistance shows up as stress, and when it's uniform, we call it pressure. Pressure is not a mysterious fluid property. Pressure is the universal consequence of constrained momentum. Once you see this, the formula P equals Fa stops being the definition and becomes the measurement. Because force per area is how you observe pressure from the outside, but the cause is inside, countless tiny momentum exchanges. Pressure is the macroscopic fingerprint of microscopic motion, and that explains why pressure behaves the way it does, why it acts in all directions, because the motion is chaotic and directionless on average. Why it increases with depth in a liquid, because pressure must increase to support weight, and weight is transmitted through pressure gradients. Why a sealed fluid transmits pressure equally, because any imbalance would create flow until equilibrium restores uniformity. Why pressure is tied to temperature, because temperature measures energy of motion, and pressure is energy of motion pushing on boundaries. And why the atmosphere can hold up a column of mercury or water, because the air, through molecular motion, is delivering momentum to the surface of the liquid, supporting it exactly like a weightless but relentless hammering. So next time you hear pressure is force over area, don't reject it. It's correct. But hear it the way you'd hear speed is distance over time. It's a measurement, not the story. The story is motion. Motion colliding, motion confined, motion redirected. Pressure is what the universe does when it can't move where it wants to. And once you see pressure that way, every balloon, every ocean, and even the air around your face stops being just there. It becomes a restless sea of motion pressing on reality. And that's the thing school didn't really teach you. They gave you the formula, but pressure isn't a formula. Pressure is a conversation between matter and boundaries, told in the language of momentum.